All right, so to complete our discussion on matrix analysis and to put a bow on the topic, I wanted to record a few short snippet videos going through some of the examples that we've discussed in class. I may be going through some of these calculations a bit quickly, but that's the beauty of YouTube. You can always pause and rewind to go through some things. And so I've got a couple of videos I want to record. The first, I want to take this example that we've done in class and I want to analyze the example start to finish using Microsoft Excel, and I want to go through some of the tips and tricks that you can use to work through this. So let's take this problem. We have our 3-bar system. We've already gone through the solution, so I think I can go through some of the intermediate calculations pretty quickly. So first thing I'll do, I'll go ahead and just make myself a little table here real quick. So we'll look at each element and let's compute the EA over L for each element just to make sure that we're all comfortable with those values. So the first one was 2,000 times 6 divided by 120. So I'm just taking each of the elements one by one and computing their EA over L's. Okay, and so we get 200 for this one. And so for element number 3, 100. So 100, 200, and 100. And this was the same thing we got during our in-class example. Okay, so our first step in our process is we need to write an element level stiffness matrix for each member and then assemble that into a global stiffness matrix for the entire system. So let's go down here a little bit. Let's see. We'll start off with element 1. So element 1 is going to be a 2 by 2 matrix. So let me sort of give myself a little region to fill that in. So we'll say that's my 1 by 1 matrix. And we know the formula is we're going to use that stiffness value and then positive. So that's the stiffness matrix for the first element. And then if we go off of our member codes here, remember this is our, if we look right here, that's our analytical model where we list the degrees of freedom. Element number 1 is connected to, or it's associated with degrees of freedom 1 and 2. So 1 and 2. So maybe what I'll do is I'll make those, I don't know, red to indicate that. Before I move on to the next element, one of the things I'm going to go ahead and do is I'm going to build a 4 by 4 matrix over here. Let's give that a different color. And what I'm going to do is I'm going to place those stiffness terms inside this big 4 by 4 matrix. So the entire system is going to be a 4 by 4, and it's going to be 1, 2, 3, 4. 1, 2, 3, 4. And what I'm going to do is I'm going to place those terms where they would go in the big system. So put that there, put that there, put that there, and put that there. And again, just 1 to 1. Like for instance, this term right here, it's in 2, 2, so 2, 2, just the same row and the same column. So that's where it would go in the big system. And then what I'll do, let me go ahead and just move this up a little bit. Move that up a little higher. Okay, and so now what I'll do is I'll copy and paste this template. So maybe we'll just copy and paste this down. And let's delete some of this, delete all this. And now let's do the same thing for element 2, right? So delete those. So what I've got here is I've still got the full-blown 4 by 4 system matrix. I've got space for my 2 by 2, but I don't have the member codes assigned because I have to go through and do that again. And while we're at it, let's go ahead and put one more down here, and let's call that K3. So there's 3 elements. Each element is going to have its own unique stiffness matrix, and it's going to have its unique position inside the global stiffness matrix. So element number 2 is going to be 200, and then that's going to be our stiffness matrix for element number 2. And then element number 3 is going to use that one. Man. Okay. And then as for where those go, well, again, it goes back to the member codes, the degrees of freedom. So element number 2, if you see here on the model, this is element number 2, and it's connected to 2 and 3, right? So this is going to be 2 and 3, 2 and 3. So those go here. So this is 2 and 2, 2 and 3, 3 and 2, 3 and 3. And I'm actually making it a point to develop the habit of doing that cell by cell, because sometimes that doesn't work. Sometimes it doesn't assemble in one big cluster. And that'll become clear on the next video that I post here in a little bit. Lastly, for element number 3, you can see this right here. I don't know if you can see the mouse pointer. This is element number 3. This connects to 3 and 4. So 3 and 4, 3 and 4. And so that goes here, 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 and here. And so now what I've done is I've figured out where each element goes in the system level matrix. So if I want to assemble, all you're doing is summing term by term. So let's make this, I don't know, let's make it a different color. And then in order to determine the system level matrix, I just say equals the sum of each of the respective terms one by one. And so as you can see here, most of those terms are empty, so it's going to be 0 plus this term up top, which is 100. But as you're going through the process, you're going to find some cells where they overlap, and you can see this pattern adds. And I'll show you what that looks like here in a second. So here's the first entry in the global matrix, and if I just copy and paste that, so I'm just using Control-C, Control-V, there you go. So for instance, if we let's say we look at this term. This term is adding up all of the like terms, and remember how we said that there's a couple values that overlap, right? Well, the 100 and the 200 overlap because those terms are at the same spot. And so it's natural that you're going to have some terms that add together. Look at joint 2 in the system. Joint 2 has 2 elements connecting to joint 2, so there should be 2 terms overlapping. And so there's your global system matrix. While we're at it, let's see, let me go ahead over off to the side. Let's use, say, this color. While we're at it, let's go ahead and do 2 more matrices. Let's go ahead and do our displacement vectors and our force vectors. So we'll call this is our displacement. Let's call this delta. I'm just going to use the letter D for shorthand, and this is F, right? So KD equals F. That's our governing equation that we're using for this problem. For the displacements, so what do we know? We know that the displacement on joint 1 and the displacement on joint 4 are 0 because those degrees of freedom are fixed. And displacement 2 and displacement 3, we don't know those, so we got to call those, just unknowns. Maybe I'll just center those up so it's a little easier to see. Maybe I'll center these up as well. Okay. As for the forces, you sort of get that checkerboard pattern. Every time that you know displacement, you don't know the resulting force because that's a reaction. And everywhere you have an unknown displacement, you know the load, right? The 300 kips is positive 300. The negative 125 kips, that's negative because it's going to the left, negative 125. So positive 300 to the right, negative 125 to the left. And this is R4 because that's an unknown reaction. And so there's our 3 sort of global entries that we need. We have our global system matrix, stiffness matrix. We have our global displacement vector, and we have our global force vector. And I'm using the term local and global, but really what I'm talking about is the assembly of the entire system. So I should say system level stiffness matrix, system level force vector, system level displacement vector. Everything's in global coordinates. We don't have to worry about local to global because that's a topic specific, for trusses and with more degrees of freedom per joint. Okay, so the next thing that we need to do, and I'm actually going to copy this down, and I'm going to actually duplicate everything. Let me delete all this. I'm just going to say equals that. So I'm duplicating the entire thing. I want a completely separate set of entries. This is Excel. You can just copy and paste that. Now I need to apply my boundary conditions. And so if you remember, when you're applying your boundary conditions, you knock out the rows and columns associated with the degrees of freedom that are fixed. And so on this problem, 1 and 4 are fixed. So we're going to knock out these. So again, rows 1 and 4, so maybe we'll do something like that. And then columns 1 and 4, columns 1 and 4 in your stiffness matrix. And again, we're knocking the columns out because those terms are ultimately going to be multiplied by 0. And we're knocking the rows out because, remember, matrix multiplication is just a way of writing equations. And those upper and lower equations we just don't really need right now because we'll use them later to compute the support reactions. Okay, so now we have a smaller system. So we've got this. So maybe I'll move that down here and I'll say that, 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 that. And then the member codes are 2 and 3. And now I've got this new system here. And then this system here. And so this, now we have new names. So now this is going to be KR. This is going to be DR. This is going to be FR. These are the reduced system level entries based on those boundary conditions. So just to make sure that we're clear on the entire process, I've wrote a stiffness matrix for each element and then assembled that into a system level stiffness matrix. And likewise, I've written system level force vectors and system level displacement vectors, and now I have applied the boundary conditions to reduce the size based on the restricted joints. And so this right here, this is really the money, if you will. This is what we're after in terms of being able to solve the problem. So what we're basically saying is that if KD equals F, or in this case, if KR times DR equals FR, well, if you look at this, the system, the money, if you will, this is what we're after. What are the unknowns? The unknowns are the displacements, okay? So to solve for the displacements, say if KR equals FR, then DR equals the inverse of KR times FR, right? So if K delta equals F, delta equals K inverse times F. I have to multiply both sides by K inverse. So in order to determine this displacement vector, what I'm going to do is this. And I'm going to do this the old way so that I know that there was some confusion on this. If you're using an older version of Excel, this method will work on both the older and the newer versions. So the way this is going to work, I'm going to start off. I'll show everybody the matrix calcs here. I'm going to highlight the entire region. I'm going to say equals matrix multiplication. So I'm doing matrix multiplication of two matrices. The first is the inverse of this 2 by 2, comma. So I close that and then comma. And then the second is this force vector. And then once your formula is written, Control, Shift, Enter. And there's your matrix multiplication. Now, just like before, Excel treats this as one array calculation, so you can't really delete one entry. You instead would have to delete the whole thing. So if you're working with arrays, just make sure that you recognize Excel treats that as one big hunk of computations. Okay, so these are the displacements, right? So now I know, in terms of the answer, maybe I'll write, some answers here. I know that D2 is 1.3 inches to the right, and it's to the right because it's positive, and then D3 is also 0.45 inches to the right because it's positive. So now we know the displacements. Now what we need to do is back calculate the forces, okay? Now let's keep in mind, and I'm actually going to copy this down here, and maybe we'll set, some equal terms here. We've already computed the individual stiffness matrices before. Like we already did them up here. So I'm just sort of being lazy and copying and paste them. So we've already got those. Maybe now what I want to do is, okay, I've got a stiffness matrix for each vector. Can I write down a displacement vector for each, I have a stiffness matrix for each element. Can I write down a displacement vector for each element? So in other words, can I write a D1, which would look something like this? Oh, it would look something like this, but it would be 1 and 2. Can I have a D2 but it would be 2 and 3. And likewise, can I write a D3, but it would be 3 and 4. So in other words, I want a displacement vector for each of those elements, and I want to get the member codes to match, the elements that I'm looking at. So let's take element number 1. Element number 1 goes from degree of freedom 1 to degree of freedom 2. I know the displacement at degree of freedom 2, that's 1.3. As for the displacement of degree of freedom 1, that's 0, right? And we had figured that out up here, right? If you look at this entry, you can see that, this is our displacement vector for the entire system. And for the system, we know that D1 is 0 because that's the joint that's fixed. So all I'm going to do now is fill in these displacement vectors and just match code for code what we had come up with before. And so once I've got these, I can then determine my F vectors, and this is just me copying and pasting the format because I'm lazy. And let's come up with a new color. Let's call those, I don't know, orange. Okay, so remember, our governing equation is K times D equals F, right? So I've got the K matrix, I've got the D vector, and so now to get the F vector, watch, just highlight equals matrix multiplication of this times that. I'm not inversing because here I've got the displacements and I'm looking for the forces. And so the stiffness times the displacement equals the forces directly. Before, when I did matrix multiplication, I was looking for the displacements, and so that's why we invert it. Here we don't need to because we're looking for that force answer. And so there you get that answer. And because I've got this set up in sort of an organized fashion, I can just copy and paste that, and there's my my three member forces. And if you recall in class, what you can do is sort of a shortcut. You can look at the second number, right? So I can look at this number here. I can look at this number, and I can look at this number, and I can write down my answers pretty easily. I know that F1 is 130 kips in tension, and I know the other two members are in compression. So we'll say member 1, 130, uh, 130 kips in tension, 170 kips compression, and there we go. Pretty easy. Now for the final component, which is determining the reactions, I actually want to show you two quick ways to do that. The first is to assemble your force vectors, okay? And this is what we did in class, right? So in class, let me remove this. So in class, we said, let's assemble these. So we had let me copy my formats down. So actually, let's fix that. Okay. So what we did in class is we said, let's assemble these vectors, right? So, this one goes here, 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 this one goes here. And that is a viable solution. So if you sum those up, let me delete this and whatnot. So if you sum these element by element, just like you did before, sum of that, that, and that, you actually get your reactions directly this way, because if you compare this force vector to what we had up here, right? So let me look at this. You can see, we got the same forces in the joints that matched, but for your reactions, we know that reaction 1 has got to be whatever that first entry is, and reaction 4 has got to be whatever that last entry is. And so we know that reaction 1 is 130 kips to the left, and we know that reaction 4 is 45 kips to the left. So I can go ahead and write that here. And so that's one way of doing it. Another way of doing it is to actually go back to the system level matrix. So if you go back to this, so watch this. Let me go back. Let me actually copy and paste this whole thing. All right, so let's reference that. So let's look at this. Okay, so let's look at this. Remember how we said that, like, this is the money, this is the big old system. Okay, so I've got the system level stiffness matrix, a system level displacement vector, and a system level force vector. Well, the displacement vector we had already figured out, right? D2 is that, D3 is that. Let me get rid of that. So here's our system level stiffness matrix, here's our system level displacement vector. One of the things you can do is you can say, let's just multiply those. Close, Control Shift Enter, and see how we're getting the same answer. Let me use some colors here. So that and that. We're getting the exact same answer in both instances. So there's two ways of determining your reactions. You can either assemble your force vectors, or you can just multiply the big old stiffness matrix times the big old displacement vector, and you will get the same answer. So either one works, okay? And that's really sort of critical when you're computing your final answer. And in terms of the final answer, I mean, this is it right here. Because again, we've got the displacements everywhere, we have the reactions everywhere, we have the internal forces in every member. And so that's how you would do this problem in Excel. I know that we did a lot of this problem by hand, and so I know I went through this a little quickly, but based on what we had done before, I figure we already have a pretty strong familiarity with this problem, so we can go ahead and just knock this one out pretty quickly. And so that concludes this. My next video, I'm going to talk about the homework assignment that you all just completed, and I want to walk through the solution to that assignment. We'll kind of do it in Excel, and we'll basically be doing the same thing. I'll probably go just at the same pace, or maybe even a little bit quicker, because we've just done this. So with that, I'm going to stop this video, and we'll move on to the next one.